Hey everyone, welcome to this explainer. Today, we're going to demystify the foundational rules governing the very things that flow all around us, meaning liquids and gases. It's a totally fascinating world of physics that we interact with every single day, often without even realizing it.
Just picture a massive sailing ship out on the ocean. Fluid mechanics is literally the science of how these huge bodies of fluids behave, both when they're at rest and when they're in motion. Whether it's the wind filling up those massive sails or the turbulent ocean pushing against the ship's hull, understanding the science means understanding the fundamental forces that shape our physical world. So, here's our game plan for today. First, what exactly is a fluid? Second, we'll look at the universal language of measurement. Third, we'll cover density, weight, and volume. And finally, number 4, viscosity and fluid flow.
All right, let's jump right into section 1. What exactly is a fluid? Defining the states of matter.
Think about a solid. The molecules are tightly packed, right? They form this rigid, compact structure that can easily resist tensile, compressive, and shear forces. But fluids? They're a completely different story. They have much larger molecular spacing. And because of this, fluids are fundamentally unable to resist shear stress. When subjected to a shearing force, a fluid just continuously deforms and changes shape. That is the very essence of flowing. It's exactly why water takes the shape of whatever glass you pour it into. Now, here's where we've got to make a slight mental leap. To really make sense of fluids, engineers use a concept called the continuum. This is the idea of a continuous distribution of matter with absolutely no voids or empty spaces. Because engineering problems involve massive, almost unimaginable numbers of molecules, we can actually just safely ignore the tiny spaces between them and treat the fluid as one continuous, unbroken block of matter. We know fluids include both liquids and gases, but they behave super differently under pressure. Think about identical syringes filled with different substances. Gases, like air, compress easily because of the massive space between their molecules. But liquids, like water, are practically incompressible under ordinary conditions. On top of that, molecular cohesion keeps liquids together, meaning they don't just expand indefinitely when you remove the pressure. That's exactly why the ocean stays in its basin instead of just floating away into the atmosphere. Moving on to section 2, the universal language of measurement, understanding SI units. Historically, different unit systems used by various scientists and countries led to a whole lot of confusion. To fix this, the International System of Units was created. These are the base SI units that scientists globally use to avoid errors when they're analyzing fluids. You've got the meter for length, the kilogram for mass, the second for time, and Kelvin for temperature. This is really the bedrock of engineering communication. But you can't just write these down however you feel like it. There are strict formatting rules here. Standard unit symbols are always lowercase, like m for meter or kg for kilogram. However, you capitalize the first letter for symbols named after real people, so it's a capital N for Newton. And when combining units into compound units, you have to insert a dot, like n.m for Newton meter. Now, here's a crucial point about how you format large numbers, and this might actually surprise you. According to SI rules, you write 50,000 with a narrow space in between the groups of 3 digits, not a comma. You will literally never see a comma used as a thousand separator in strict SI engineering documents. All right, let's get into section 3, density, weight, and volume, the physical properties of fluids. The first major property is mass density, which is simply the mass possessed per unit volume. Imagine a space with just a few molecules bouncing around. That's a low-density fluid. Now imagine packing tons of molecules into that exact same space. That's high density. This perfectly illustrates why adding pressure forces more molecules into the same space, increasing the overall density. Conversely, if you raise the temperature, molecular spacing increases and the mass density drops. But mass density isn't the whole story. We also have specific weight. While mass density is really just about the amount of matter in a space, specific weight actually factors in gravity. It's the weight possessed per unit volume, and because it relies on gravitational acceleration, a fluid's specific weight will genuinely vary from place to place. Water literally has a slightly different specific weight depending on exactly where you are standing on the globe. To make life a bit easier, engineers use a brilliant shortcut called specific gravity. It's the ratio of a fluid's specific weight compared to a standard fluid, which, for liquids, is pure water at 4 degrees Celsius. Because it's a ratio, specific gravity is a pure number without any units at all. For instance, the specific gravity of mercury is 13.6. That simply means it's 13.6 times heavier than our standard of water. It's just a really handy, universally understood shorthand.
And that brings us to Section 4, viscosity and fluid flow. How fluids resist movement.
So viscosity is a fluid's resistance to flow. It's essentially the internal friction between adjacent layers of the fluid. Water, for example, pours freely and easily with a really low viscosity of just 1.0 centipoise. But honey? Honey has massive internal friction. It registers at a staggering 12,200 centipoise, which is exactly why it resists deformation and pours so incredibly slowly. Viscosity isn't a static trait, though. It definitely changes based on the environment. Generally, liquids have a much higher viscosity than gases. But interestingly, if you raise the temperature of a liquid, its viscosity drops significantly. The source notes that water's viscosity falls from 1.79 centipoise near freezing all the way down to just 0.28 at boiling. Pressure increases liquid viscosity too, but practically speaking, you don't even have to worry about that effect unless you're under an extreme crushing pressure of over 40 atmospheres. Because flow behaves in pretty predictable ways for a lot of substances, we classify them. Common fluids like water, air, and mineral oil are known as Newtonian fluids. This just means they obey Newton's law of viscosity. For a Newtonian fluid, viscosity is a reliable constant as long as the temperature stays the same. It doesn't matter how fast you stir it or how much shear stress you apply, its fundamental resistance to flow remains exactly the same. But of course, that reliability isn't universal. The source text leaves us with a totally fascinating cliffhanger by mentioning time-independent non-Newtonian fluids. These are substances whose viscosity actually changes under stress. Just imagine a fluid that thickens up the harder you push it. So I'm going to leave you with this final question to wonder about. How bizarre does physics get when a fluid flat out refuses to play by Newton's rules? Thanks for exploring the properties of fluids with me in today's Explainer, and keep questioning the world around you.